H2O, M, CH3, 3 polymer surface functionalization, creation of composites, diffusion barriers, etc. ALD on particles 25-100 degree C for polymer particles, 100-400 C for metal forward/alloy particles BN, ZRO2, CNTs, polymer particles. Various gases, fluidized bed reactors are used to allow coating of individual particles, deposition of protective and insulative coatings, optical and mechanical property modification, formation of composite structures, conductive mediums. Plasma or radical enhanced ALD for single element ALD materials 2800 degree C pure metals, i.e. Ta, T, Si, Ge, Ru, Pt, metal nitrides, i.e. tin, tan, etc. Organometallics, MH2Cl2, tert-butylamidotris, diethylamido, tantalum, ptite, bis, ethylcyclopentadienyl, ruthenium, NH3 drum structures, MOSFET and semiconductor devices, capacitors. Plasma enhanced ALD of metal oxides and nitrides 2300 degree Cl2O3, SiO2, ZNOx, inox, HFO2, SiNX, TaNX similar to thermal ALD. Applications, edit. Microelectronics applications, edit. ALD is a useful process for the fabrication of microelectronics due to its ability to produce accurate thicknesses and uniform surfaces in addition to high-quality film production using various different materials. In microelectronics, ALD is studied as a potential technique to deposit high permittivity, gate oxides, high memory capacitor dielectrics, ferroelectrics, and metals and nitrides for electrodes and interconnects. In high gate oxides, where the control of ultra-thin films is essential, ALD is only likely to come into wider use at the 45 nm technology. In metallizations, conformal films are required. Currently it is expected that ALD will be used in mainstream production at the 65 nm node. In dynamic random access memories, DRAMs, the conformality requirements are even higher, and ALD is the only method that can be used when feature sizes become smaller than 100 nm. Several products that use ALD include magnetic recording heads, MOSFET gate stacks, DRAM capacitors, non-volatile ferroelectric memories, and many others. Gate oxides, edit. Deposition of the high oxides Al2O3, ZrO2, and HFO2 has been one of the most widely examined areas of ALD. The motivation for high oxides comes from the problem of high tunneling current through the commonly used SiO2 gate dielectric in MOSFETs when it is downscaled to a thickness of 1.0 nm and below. With the high oxide, a thicker gate dielectric can be made for the required capacitance density, thus the tunneling current can be reduced through the structure. Transition metal nitrides, edit. Transition metal nitrides, such as tin and tan, find potential use both as metal barriers and as gate metals. Metal barriers are used to encase the copper interconnects used in modern integrated circuits to avoid diffusion of Cu into the surrounding materials, such as insulators and the silicon substrate, and also to prevent Cu contamination by elements diffusing from the insulators by surrounding every Cu interconnect with a layer of metal barriers. The metal barriers have strict demands. They should be pure, dense, conductive, conformal, thin, have good adhesion towards metals and insulators. The requirements concerning process technique can be fulfilled by ALD. The most studied ALD nitride is tin, which is deposited from TCl4 and NH3. Metal films, edit. Motivations of an interest in metal ALD are 1. Cu interconnects and W plugs. or at least Cu seed layers for Cu electrodeposition and W seeds for WCVD. 2 transition metal nitrides, for example tin, tan, Wn, for Cu interconnect barriers. 3 noble metals for ferroelectric random access memory, FRAM, and drum capacitor electrodes. 4 high and low work function metals for dual gate MOSFETs. Magnetic recording heads, edit. Magnetic recording heads utilize electric fields to polarize particles and leave a magnetized pattern on a hard disk. Al2O3 ALD is used to create uniform, thin layers of insulation. By using ALD, it is possible to control the insulation thickness to a high level of accuracy. This allows for more accurate patterns of magnetized particles and thus higher quality recordings. Drum capacitors, edit. Drum capacitors are yet another application of ALD. An individual drum cell can store a single bit of data and consists of a single MOS transistor and a capacitor. Major efforts are being put into reducing the size of the capacitor, which will effectively allow for greater memory density. In order to change the capacitor size without affecting the capacitance, different cell orientations are being used. Some of these include stacked or trench capacitors. With the emergence of trench capacitors, the problem of fabricating these capacitors comes into play, especially as the size of semiconductors decreases. ALD allows trench features to be scaled to beyond 100 nm. The ability to deposit single layers of material allows for a great deal of control over the material. Except for some issues of incomplete film growth, largely due to insufficient amount or low temperature substrates, ALD provides an effective means of depositing thin films like dielectrics or barriers. Photovoltaic applications, edit. The use of ALD technique in solar cells is becoming more prominent with time. In the past, it has been used to deposit surface passivation layers in crystalline silicon, Si, solar cells, buffer layers in copper indium gallium solnide, 6, solar cells and barrier layers in dye-sensitized solar cells, DSSCs. For example, the use of ALD-grown Al2O3 for solar cell applications was demonstrated by Schmidt et al. It was used as a surface passivation layer for the development of PERC, passivated emitter and rear cell, solar cells. The use of ALD technique to deposit charge transport layers, CTLs, is also being explored widely for perovskite solar cells. The ability of ALD to deposit high-quality and conformal films with precise control on thickness can provide great advantage in finely tailoring the interfaces between CTL and perovskite layer. Moreover, it can be useful in obtaining uniform and pinhole-free films over large areas. These aspects make ALD a promising technique in further improving and stabilizing the performance of perovskite solar cells. Electro-optic applications, edit. Thin film couplers, edit. As photonic integrated circuits, PICs, emerge, often in a manner similar to electronic integrated circuits, a wide variety of on-chip optical device structures are needed. One example is the nanophotonic coupler that behaves as a micrometer-size beam splitter at the intersection of optical waveguides, in which high aspect ratio trenches, 100 nm width x 4 micrometer depth, are first defined by etching, then backfilled with aluminum oxide by ALD to form optical quality interfaces. Biomedical applications, edit. Understanding and being able to specify the surface properties on biomedical devices is critical in the biomedical industry, especially regarding devices that are implanted in the body. A material interacts with the environment at its surface, so the surface properties largely direct the interactions of the material with its environment. surface chemistry and surface topography affect protein adsorption, cellular interactions, and the immune response. Some current uses in biomedical applications include creating flexible sensors, modifying nanoporous membranes, polymer ALD, and creating thin biocompatible coatings. ALD has been used to deposit TO2 films to create optical waveguide sensors as diagnostic tools. Also, ALD is beneficial in creating flexible sensing devices that can be used, for example, in the clothing of athletes to detect movement or heart rate. ALD is one possible manufacturing process for flexible organic field effect transistors, OFETs, because it is a low-temperature deposition method. Nanoporous materials are emerging throughout the biomedical industry in drug delivery, implants, and tissue engineering. The benefit of using ALD to modify the surfaces of nanoporous materials is that, unlike many other methods, the saturation and self-limiting nature of the reactions means that even deeply embedded surfaces and interfaces are coated with a uniform film. Nanoporous surfaces can have their pore size reduced further in the ALD process because the conformal coating will completely coat the insides of the pores. This reduction in pore size may be advantageous in certain applications. As a permeation barrier for plastics, edit. ALD can be used as a permeation barrier for plastics. For example, it is well established as a method for encapsulation of OLEDs on plastic. ALD can also be used to inoculate 3D printed plastic parts for use in vacuum environments by mitigating outgassing, which allows for custom low-cost tools for both semiconductor processing and space applications. ALD can be used to form a barrier on plastics in roll-to-roll processes. Quality and its control, edit. The quality of an ALD process can be monitored using several different imaging techniques to make sure that the ALD process is occurring smoothly and producing a conformal layer over a surface. One option is the use of cross-sectional scanning electron microscopy, SEM, or transmission electron microscopy, TEM. High magnification of images is pertinent for assessing the quality of an ALD layer. X-ray reflectivity, XR, is a technique that measures thin film properties including thickness, density, and surface roughness. Another optical quality evaluation tool is spectroscopic ellipsometry. Its application between the depositions of each layer by ALD provides information on the growth rate and material characteristics of the film. Applying this analysis tool during the ALD process, sometimes referred to as in situ spectroscopic ellipsometry, allows for greater control over the growth rate of the films during the ALD process. This type of quality control occurs during the ALD process rather than assessing the films afterwards as in TEM imaging, or XR. Additionally, Rutherford backscattering spectroscopy, RBS, X-ray photoelectron spectroscopy, XPS, Auger electron spectroscopy, AES, and four-terminal sensing can be used to provide quality control information with regards to thin films deposited by ALD. Advantages and limitations, edit. Advantages, edit. ALD provides a very controlled method to produce a film to an atomically specified thickness. Also, the growth of different multilayer structures is straightforward. Because of the sensitivity and precision of the equipment, it is very beneficial to those in the field of microelectronics and nanotechnology in producing small, but efficient semiconductors. ALD typically involves the use of relatively low temperatures and a catalyst, which is thermochemically favored. The lower temperature is beneficial when working with soft substrates, such as organic and biological samples. Some precursors that are thermally unstable still may be used so long as their decomposition rate is relatively slow. Disadvantages, edit. High purity of the substrates is very important, and as such, high costs will ensue. Although this cost may not be much relative to the cost of the equipment needed, one may need to run several trials before finding conditions that favor their desired product. Once the layer has been made and the process is complete, there may be a requirement of needing to remove excess precursors from the final product. In some final products there are less than 1% of impurities present. Economic viability, edit. Atomic layer deposition instruments can range anywhere from $200,000 to $800,000 based on the quality and efficiency of the instrument. There is no set cost for running a cycle of these instruments. The cost varies depending on the quality and purity of the substrates used, as well as the temperature and time of machine operation. Some substrates are less available than others and require special conditions, as some are very sensitive to oxygen and may then increase the rate of decomposition. Multi-component oxides and certain metals traditionally needed in the microelectronics industry are generally not cost-efficient. Reaction time, edit. The process of ALD is very slow and this is known to be its major limitation. For example, Al2O3 is deposited at a rate of 0.11 nm per cycle, which can correspond to an average deposition rate of 100-300 nm per hour, depending on cycle duration and pumping speed. This problem can be overrun by using spatial ALD, where the substrate is moved in space below a special ALD showerhead, and both the precursor gases are separated by gas curtains /bearings. In this way, deposition rates of 60 nm per minute could be reached. ALD is typically used to produce substrates for microelectronics and nanotechnology, and therefore, thick atomic layers are not needed. Many substrates cannot be used because of their fragility or impurity. Impurities are typically found on the 0.11% because of some of the carrier gases are known to leave residue and are also sensitive to oxygen. Chemical limitations, edit. Precursors must be volatile, but not subject to decomposition, as most precursors are very sensitive to oxygen /air, thus causing a limitation on the substrates that may be used. Some biological substrates are very sensitive to heat and may have fast decomposition rates that are not favored and yield larger impurity levels. There are a multitude of thin film substrate materials available, but the important substrates needed for use in microelectronics can be hard to obtain and may be very expensive. References, edit. 1 carat chromers.